Well, good evening. It is evening now. Friends and colleagues, ladies and gentlemen. The IMS public lecture is an outreach activity of the NUS Institute for Mathematical Sciences. This evening, we are honored to have Professor Fanghua as a speaker. Professor Lin is a Silver Professor of Mathematics at the Courant Institute of Medical Sciences, New York University. He obtained his PhD from the University of Minnesota in 1985. Thereafter, he joined the Courant Institute as an instructor and was awarded the Silver Professorship in 1989, 4 years after his PhD, after a short stint as full professor at the University of Chicago. His research interests include analysis, partial differential equations, and geometric analysis. He continues the Courant tradition of applying hard analysis to nonlinear partial differential equations and has established himself as a world leader in the field. He has published over 150 papers, supervised 11 PhD students, and 20 postdocs. He is currently on the editorial board of over 10 journals, including these prestigious journals: Communications on Pure and Applied Mathematics, Science Journals of Mathematical Analysis, Journal of Differential Geometry, and Mathematical Research Letters. Professor Lin has received many honors and awards, and these include the Sloan Fellowship in 1989, the Presidential Young Investigator Award from 1989 to 1994, the Changjiang Professorship at Zhejiang University in 1999, the American Mathematical Society Bogner Prize in 2002, election to the American Academy of Arts and Sciences in 2004, and the S.S. Chen Prize in 2004. He was an invited speaker at the International Congress of Mathematicians in 1990. That was in Zurich, right? 1990 was in Zurich? Okay, yes, good. 94 was in Zurich. An invited speaker at the American Mathematical Society National Meeting in 2002, and a plenary speaker at the International Congress of Chinese Mathematicians in 2004 and also in 2007. All right? Okay. So it is now my great pleasure to invite Professor Lin to deliver his public lecture entitled Roles of Differential Equations in Mathematics and Sciences.
Well, first, thanks Professor Louis Chen for this wonderful introduction. And I also want to take this opportunity to thank the Mathematics Department of the National University of Singapore, and also the Institute of Mathematics, Institute of Mathematical Sciences of the National University of Singapore, so Professor Louis Chen and Professor Bob in particular. Well, as a mathematician, we often know, in fact, it's rather difficult to explain what you do, even to your own colleagues. And to explain that to public, I know it is extremely a challenge. I did spend quite a bit of time to prepare these slides and spend a lot of time, in fact, think about it. But I won't be surprised that my effort here may be quite dismal. On the other hand, I just want to get a few points across here in this public lecture. So hopefully you have a patience to bear through my lecture. In any case, I thank you very much for coming. So, first, let me start. What is a partial differential equation? Now, for some of you know, of course, quite a lot, and for some of you maybe never even hear the words of a partial differential equation. And here's one. You don't have to know that, what it means. It doesn't matter. Give us a picture or something. So here's one, and it's quite a simple partial differential equation, but it's a very difficult partial differential equation too. So what is a partial differential equation? you can simply view as a simple relation which involves some unknown quantity that we call a function, and it's changing of rate respect to various variables that the function depends on. And that usually called the partial derivatives. Because the quantity, say for example, may depend on temperature, right? May depend on time, may depend on position. And in Euclidean space where we stay, you have the three directions to go. So there is a rate of changing of this unknown that we call the function respect to various directions, and that's called the partial derivatives. So partial differential equation is simply a relation between this unknown function and the derivatives. It is very much like an algebraic equation. Here's one is a quadratic equation, and I cook up in this way, at least you can guess one root right away. Yeah, when equation has x as 1, right, as a solution. And then become, you factor out, become a linear equation, then it's very easy to find another root. There could be an exercise for elementary school students, I suppose. Particularly in Singapore, elementary school students are very, very smart. So therefore, like very much like algebraic equation, the partial differential equation can also be linear, quadratic, or generally non-linear. Now, from our experience in elementary school, the linear equation always easy to solve. Yeah, I think most people can do that in third grade or something like that. Much easier to solve than the non-linear ones. So, therefore, in our business, I refer to us as we're doing partial differential equation, and people will usually ask what you do. We always emphasize we are doing non-linear partial differential equation. So that way we will impress our colleagues at least. Yeah? I'm doing something very non-linear partial differential equation. And most time actually we're doing very much linear equation or perturbation of that, but we won't tell the people. Okay? So that is more or less sort of the introduction of what is the partial differential equation. Now, let me go over the history a little bit. It's an old subject, partial differential equation. It's born right after Newton, Leibniz created the subject of calculus. Okay, whenever calculus, soon after that, you have differential equations. Ever since from the very beginning, the first partial differential equation or differential equation was written, that already the subject, you know very well, has a sort of two rules played by that particular subject. The one is it is central, I call it central to mathematical analysis. In classical mathematics, usually divides into three disciplines: analysis, algebra, and geometry, roughly speaking. So PDE, very soon after calculus, became very central to the development of mathematical analysis. In fact, one of the sort of very, very first partial differential equation is described by the heat conduction phenomena called the heat equation. And the way to solve it use Fourier series. And Fourier series, understanding of so-called Fourier series or Fourier integrals is the beginning of the subject of harmonic analysis. And in fact, all the rate subject development of harmonic analysis has a lot to do with the theory of partial differential equation. But partial differential equation not only is central sort of to the mathematical analysis, and particularly over the last 2 or 3 decades, and it's remarkably useful and important to other branches of the pure mathematics. Now, this picture probably appeared in the last public lecture of Professor Sir John Ball. This is Geisha Pelman. Well, I purposely put on his picture here. We now more or less agree that he solved the Poincare conjecture. Okay. I'm not sure the people all agree that he solved the geometrization conjecture yet. But people have not found much sort of mistake, but people haven't completely agreed either. Okay? So I won't say that. There should be something that Sir John Ball probably have already talked about. But why I put his picture on? Because the principal tool he used is use nonlinear partial differential equation on manifold to solve a non-historical problem in topology. Okay? But his work is not the first example. But it's a remarkable example that he used partial differential equation again and to solve one of the deepest problems and most difficult problems in topology. But you can hear me, right? Yeah, I can. My voice is enough. Later on, it's difficult. But on the other hand, if you go back 10 years or 20 years, you find many fundamental works in topology, in geometry, was done by partial differential equation. So let me mention a few works. For example, the work of Simon Danielson, which dealing with so-called Young Mills. And they're dealing with study of the four-dimensional topology. The space we stay is three-dimensional. If you add time, additional dimension, then it will be four-dimensional space. So in general, four-dimensional manifolds are fascinating, very important. And the Young Mills use the Young Mills or partial differential equation to understand the topology. That is the main work of Danielson. Danielson receives Fields Medal because of that work. But over last several Fields Medals, Terry Stahl, bigger portion of his work is on nonlinear partial differential equation. John Bourgain, the previous one, got the Fields Medal. Part of that reason is because his contribution in nonlinear partial differential equation, and of course harmonic analysis and a lot of other things. And in particular, Perry-Lyons got a Fields Medal also because partial differential equation, the contribution he made. Okay? But many more. The work of Tobbs, for example, Tobbs and Danielson recently won Shaw Prize. Tobbs proved equivalence between, say, Selby-Whittle invariant and Gromov invariant, and uses purely bigger portion of that is partial differential equation. And our famous Chinese mathematician S.T. Yao proved the Calabi conjecture is solved one of the equations I write down, but in complex variable, called the complex non-Jean-Pierre equation. So I think I convince you partial differential equation is very important and useful in pure mathematics. In fact, we impressed a lot of our colleagues in topology, in geometry, and so on. They don't believe that, at the end they have to understand part of the partial differential equation. But this is part of the mathematics, where partial differential equation plays an important role. But partial differential equation from very, very beginning has always another rule, which is the principal mode of analysis studied in many branches of science, particularly in physical sciences. I will give you many examples of many equations just named later. Now the lecture, the good thing about it is you're not going to see any partial differential equation. That is only one good news about the lecture. Okay, so because of these two double rules played by partial differential equation, and therefore the subject had to meet various needs and challenges. And because of that, the study of partial differential equation has become a huge, complex, and diverse field. That is one very good news. We should feel very happy about working in this field. But there's a price to pay. The price to pay is the next paragraph. In truth, there is no central core theory of partial differential equation. Nor can there be. There is more assertive, which I believe also. Okay? You can say this is my personal view. That is the view of most people working in the field. Okay? The reason is each partial differential equation, particularly nonlinear, because nonlinearity describes particular and natural phenomena. And because of that, you ask a particular set of questions, and therefore require a particular set of techniques and methods. So the questions and the methods solving with nonlinear partial differential equations are different from problem to problem. It's nothing surprise, okay? But that is, however, a big challenge for people in the field. That is why I say it's sometimes even very difficult to talk to people, say, work in the same field, partial differential equation, because we speak completely different foreign languages, okay? Now, I had an interesting conversation with late Professor S.S. Chen in '86 spring. Well, he just retired, but he still was at MSRI. He built MSRI. And he was very, very dear and good friend of Professor Louis Nemler at Courant Institute. So I was postdoc of Louis Nemler, and I went to Berkeley. I spent half a year. So the first thing Professor Chen asked me, he always impressed by people working in partial differential equation. How can you be so diligent and so persistent? Because the reason he observed that each nonlinear partial differential equation, in particular, partial differential animal, always seems to work, only being able to work on one or two or at most type of problems or equations. So it seems like ever since you graduate, you simply married to one PD for the whole life. Now, how can you do that? If you choose wrong marriage, and this life is over, basically, right? So he asked me, why you have this kind of college? How do you know that you choose the right problem? And I don't have a very good answer, particularly by then, and even so many years later. That is still a philosophical point that we can discuss, of course, at other time. Okay? But think about it, it is true indeed. And here is simply a non-complete list of important partial differential equations. And I can guarantee you, even the best nonlinear partial differential analysts probably can work only one or two or three maximum sort of type of partial differential equations on the list here. So we have hyperbolic, wave equation, parabolic, heat equation, elliptic, and then you have Schrödinger-Dirac, KdV, related to integrable system. So these are types of equations, and then you have non-local solar differential operators and other things. And from classical fluid and mechanics, you have Euler, Navier-Stokes, Hamilton, Jacobi, and kinetic theory, now very popular. And you have from condensed matter physics, all these famous equations. And these are related to more pure mathematics. Euler, Lagrange, Monge-Ampere, Liouville, Cauchy-Riemann. Okay? Now these are study pattern formulations, particularly in biology, very popular. Species competitions and so on. And these study classical field and relativity and so on. And you can list the going, it's not complete. You can list going on and going on, going on. There are many, many equations. And each of us spend a lifetime probably on one type or two type of equations at the most. Okay? And no wonder many people do not want to do that. Yeah? Once I hear, like a mathematician, first you have to be smart in order to be successful. Second, you have to work very, very hard. You have to work very, very hard. And third, you have to prepare that you may do nothing by the end of your life. Okay? And that is the worst. Okay? So, but it's not so dramatic, of course. Yeah. And as you can see, I'm still enjoy very much to be a mathematician. All right. So there are a lot of other good things, which we won't tell you. Yeah. And here are some famous quotes which related to my discussion. Okay. So the first one is Einstein. He said he does not want to become a mathematician because of so many interesting, beautiful problems and important problems in mathematics. And because of that, we will pursue that in this essential one. Okay? That is his view. And whether you're depressed or not, to reach out find mathematics is trivial. But you say, I can cannot work without it. I'm not going to comment further. You can think about all these comments. And here, these two are promoting mathematics. I didn't know that GIPS has a step. But, it's interesting. IMS has a GIPS lecture, right? So human mind has never invested in life-saving machine like algebra. And here, Eugene Wegener, he seems always favor mathematics, believe it or not. And here is come from his article in 1959, 50 years ago at the CPM. It's one of his lecture, the unreasonable effectiveness of mathematics, come from his lecture. And there is one paragraph which says that. Okay? You can, well, there's an interesting comment also, but for English later, but probably not much to do with my talk, but I thought it was interesting anyway. So, okay. Now, so we have so many problems and all these comments. We have so many partial differential equations. So you can only work on one or two in general, right? However, in fact, there is a well-defined seed in classical theory. Okay, so I go back to classical seeds. So the first unified seed seems to be, for many, many years, at least last for 100 years, for the subject, is so-called well-posedness. In other words, when you see a partial differential equation, these are most common questions people will ask, or mathematicians will ask, or will do first. So first, you give a partial differential equation, you say whether or not it has a solution. Now, to a physicist or to an engineering, that is one of the most stupid questions you ask. Because whenever they lay down equation, of course they know there's a solution. Okay, they already cook up a special solution before they made up of this equation. Okay, but there is more general existence. Mathematics could be different. Okay, so the existence turns out to be always a question. Okay, and in many other cases, existence is not clear. For example, problem from geometry or other issues, calculus variation. It's also clear that we always have a right solution we want to work with. And then uniqueness often deal with that dynamical sort of situation. Now, for ODE, of course, it's well known. You prescribe initial position, prescribe the initial velocity, and if you know the force field, and then of course the trajectory of this particle will be uniquely determined. This is a Newtonian law. Right? So existence and uniqueness, for many questions, it's very, very clear. But for uniqueness, in fact, some of the most fundamental partial differential equation is still unknown. Now for calculus variation, uniqueness is not rating to ask, in fact. In most of cases that you know, for example, a lot of local minima, the landscape of energies could be very, very complex, okay? And you can have saddle points, could be also solution. And even an absolute minima may still not be unique. And even the situation is very genetic, may be still not unique. Okay? So uniqueness is depend on question. But for evolution equation or dynamical case, that you expect if that is the right equation, describe the right physical phenomena, the solution should be unique. Okay? Now related to that is also called the regularity issue. That is never a classical issue, but over the development of the theory over the years, people realize it is intimately connected. When you talk about solution existence, you will say, what kind of solution you're asking for? Okay, that has to do with class of the solutions that is related to regularity. Because the uniqueness has something to do with regularity. Okay. And then continuous dependence. That is always the case with stability. Because the measure, any problem, reasonable problem from physics or application, if you change the data a little bit, if you change the measurement a little bit, because you always make errors. If the solution drastically changing, then you should ask yourself whether or not that is the right model. Okay, so that is classical Habermas well-posedness. And basically, even though the partial differential equation could be completely different. The way you treat each differential equation could be completely different. People seem to ask all these standard questions in first place. And that occupies any time before maybe 1960, the theory of partial differential equation basically stayed within these kind of questions. Okay? All right. Now, let me say a few words about existence and regularity. Existence of good solution in geometry is extremely important. For example, existence of the solutions, good solution to Yamabe equation, which I'm not going to say what it is because there's no point to write it, or to point to explain what is this equation. It's related to so-called the uniformization by conformal geometry. Okay, existence of certain spatial constant scalar curvature metric. Existence of non-Yang equation related to so-called existence of the Einstein metric. And in complex case, there is a whole series now developed with Clapeyron manifold. The reason the Miller symmetry or everything started with Clapeyron manifold. So existence of good solution led to in geometry some fundamental object. Okay? For example, minimum surface related to positive mass theory in general relativity. So you never expected that. But positive mass theory in general relativity is something which, everybody accepted. But the precise mathematical proof related to the theory of minimum surfaces. And a more quantitative version of positive mass theory called Hanel's inequality is also related to minimum surface theory and its dynamic. More related to dynamic. So Yang-Mills, I explained a little bit. The Danielson theory, I said a little bit, his physical work related to Yang-Mills. And he established the number of solutions related to the topology in genetic cells. So that is understanding the so-called module space or solution space of that related to the topology. And related to the Gromov-Witten invariant is established the property of the Silberg-Witten function. And that is work on TOPS. So these are very, very fundamental works in over the last, say, 2 decades or something or more in geometrical analysis, geometric topology, and so on and so forth. Seems all related to the basic existence and the regularity theory of certain non-linear partial differential equation on manifold. Okay. So these are examples. I should control time. Is this watch right? So let me talk about uniqueness and continuity dependence. So very usually evolve the dynamical system evolution equation. Okay? So for example, stability of Minkowski space-time. So what is the issue? So if we live in flat Euclidean space and we have a nice time. Okay? Then of course that is forever. It's ideal world. Now if you give a small, very small perturbation of that, small and we never change like far away, just say on Earth did a tiny little bit thing, whether or not it will affect the global existence of the space-time. Okay? And the theorem says by Christodoulou and Serge Klaineman, they say that is true. So that is a simple mathematical statement. And if we talk to physicists, of course, it must be true. There's no other reason. What else can be, right? It has to be true. But the proof of that, original proof, takes more than 500 pages. Now, I do not want to threaten a young student. I mean, if you started a nonlinear partial differential equation, spend, say, 2 years at least to study this subject, then you read a paper which is 500 pages. Okay, after that, you still don't know what to do. So that is something challenge already. This thing I will address a little bit later. But of course, this proof now simplified to about 1/10 of its length, about 60 pages. But still involve other things. Okay, so it's a very technical paper at that time. It's about now almost 20 years ago, the paper. Now, open problem is the uniqueness and continuity dependence is still open for Euler and the Navier-Stokes equation. And the related problem is the Boltzmann equation. That is still open. And I believe if one can solve one of these, the other will be done too. It's closely related. It's just a two-type with more or less similar type of equation in different scale. We talk about multi-scale everything. Okay? And the first one listed as a millennium problem was $1 million price tag on that problem. So let me just describe briefly that problem. Okay? So just for fun. Okay. So here is the equation of Euler. I'm sorry. Equation of Euler, which laid down 252 years ago exactly. Yeah, by Euler. Well, Euler was 50 years old. So that is the equation. You don't have to understand. I'm not going to explain that. But with such a small box, let me tell you, this is a simple partial differential equation, right? We can write down equation that several pages cannot fit. But that is a very simple partial differential equation. And it's quite easy to understand what it's all about. Okay. So, and with this Navier-Stokes equation, the only difference is so-called adding viscosity of the fluid. Okay. And this is due to Navier-Stokes. It's probably about 100 years later in Euler's original equation. So one is about 252, the other is about 170 years old, the two equation. All right, so these two partial differential equations. So what kind of question we want to ask the millennium dollar question? Okay, $1 million question. And it's the following one. And it's the simplest. It's like a particle problem. Give initial position and initial velocity, and give this equation, so that like Newtonian law. But what Euler's equation exactly is in some sense is a Newtonian law for fluid. Okay, so give this physical law, and then you ask whether or not we have this global solution, smooth solution for that problem. Okay, this is called a Cauchy problem. So if you have a smooth solution, then the solution will be unique even on all the data solutions. We talk about data solutions. Right? So the first question, philosophical question, pretend don't know anything about partial differential equation. And seriously, the problem being attacked at least over 70 years. So one generation of mathematician about usually 10 to 15 years. Okay, we know mathematician one generation is different from human one generation. Well, mathematician one generation is about 10 to 15 years. Okay? So that means at least 5 to 7 generations of mathematicians. And I can assure you, practically, probably more than 80% or 90% best analysts will think about this problem in lifetime for a period of time. Everybody will try to see if you can do something about it. But still open. Okay? Why the problem is so difficult? Well, in mathematics, yeah, or in other science problems, people usually ask these kind of questions. Why it is difficult? Well, in mathematics, people say, if I know why it is difficult, then I can solve it. Yeah? And engineering will say, if anything possible, please tell us that you can build, we will build. Right? So mathematics say, if you tell me exactly what's the difficulty, then I will be able to solve it. Well, maybe we don't know the difficulty. But we actually know quite much about the difficulty of these problems. But we still don't know how to solve. And that is magic about this problem. A simple equation. Okay. Now you ask another philosophical question. Are these equations right? Okay? Or are we working on the right problem? Now, so are these equations right? Now I have this painting here. So that in artistic mind, there's motion of the stars and the moons and so on. Interesting picture. In Van Gogh's picture of the starry is even more better. But I just pick up any one looks like. But does this picture familiar to some of us here? That we work on superfluid. Then we work on superfluid. Superfluid means really micro-size, small, tiny things, or even nanoscale. We see vortex dynamics like that kind of picture. And that is supposed to be like a universal picture. This is a star dynamic. So if Euler equation is correct, then it describes the motion of the stars. It also describes the vortices motion in superfluid. So from nanoscale to scale of the universe, this is the equation given by God. You shouldn't call the equation of Euler, but the equation of God. But what this means? Now, for a mathematician, we always know if a problem involves multi-scale, it's become very difficult. But what this indicates is Euler equation contains every scale, a continuous scale. Because if Euler equation is right, you do describe that. And you just produce recent work, which again is 700 pages long. And the superfluid semi-class, again, you have this kind of picture. Okay? You can debate. There must be some collection because we work on the right problem. Because after all, you cannot use Euler equation to describe, say, interaction with fluid and the air. But something related to that, you can have such chaotic phenomena. You can have vortex. This is the Catalina picture, hurricane picture. All these phenomena show one way or other contained in the Euler equation behavior or approximate of that. Okay? And indeed, numerical computation does indicate these things. So you will say, are these equations right? You can don't believe that or you suspect that. It's natural. But if you start to unbelieve or suspect Euler equation, then your life in very deep trouble. Why? Because if you don't believe Euler equation, then you should suspect conservation law. If you suspect conservation laws, I don't know how much physics will survive or natural laws will survive. And if you suspect Euler equation, then you don't believe Newtonian law. Okay, these are in classical regime. And Euler equation, in fact, is simply conservation of momentum, conservation law. And that is one hand, still phenomenological. We say, well, there must be some collection. You can start with molecular dynamic, and then you do a reasonable mathematics and quite a reasonable assumption. You derive Euler equation. It's contained. Or you add a little bit of noise, even in computation or in statistical physics, you still derive Navier-Stokes equation, very Navier-Stokes. That has been done in 1980s. Okay? And we have much more. But you can derive Euler equation from Boltzmann equation. So if you don't believe Euler equation, then you should suspect Boltzmann equation. And this picture of Boltzmann, exactly, he does not have a padding 4 in field computer code. If he has that, the whole kinetic theory probably will be done 100 years ago. Okay? But anyway, there's latest proof in 1990s that from kinetic theory Boltzmann equation, you can derive Euler equation under very reasonable assumption. So if we don't believe Euler equation or Navier-Stokes equation as a fundamental equation describe fluid dynamic phenomena, we really in a very difficulty sort of dilemma. What are we going to do in science? Okay. Of course, I'm a mathematician. I can disregard all the laws in science. I say I'm simply interested in mathematics. And here is a simple Euler equation. Can you do it or not? After all, most of number theory problem is like that, right? Just do that. It's challenge to human ability to solve some problems. A simple, doesn't matter whether or not it describes real science. But this is another philosopher, of course, another story. But anyway, Euler equation is fascinating and it's difficult. So let us detour a little bit. And this is a list of, clearly not complete list of names of mathematicians who certainly made important contributions to this incomprehensible Navier-Stokes and incomprehensible Euler equation. I'm not going to say, of course, all these words. All right. So that is a detour about the story of the Euler equation. I thought that this is another millennium problem because we talk about Poincare conjecture, which is being solved. Whenever a problem is solved, it's no longer interesting in some way. Okay, unless we find something more interesting to work with. And Navier-Stokes still open, so we should talk a little bit more here. So here is a challenge, really, to us, to people working in the field, and to people even in general math community. Partial differential equation theory, and that issue we discussed in the panel discussion today. You can only study very simplified problem or models, and sometimes oversimplified, which omit a physical interest in 11 parameters. So that is one challenge, and you have to work with problem, a real problem, more close to real world. And indeed, and that is done by computer, and computer understand better than us, right? And because the introduction of computing capability, and actually the whole science game is completely changed. The way we do science is different. The computational material science, this is a workshop of this name, is because part of the reason, of course, a lot of interest in computer science, numerical simulation, mathematics, but much, much more. Because, for example, in Singapore, you probably don't have a lot of heavy equipment to do a lot of basic research because it's way too expensive and it's redundant. If somewhere already in the world have this equipment, why you buy again, right? Computer can help because you have some experimental data. After all, www tell you practically everything. You Google it, right? And so you have some experimental data. But computer really can tell you all the parameters to do the simulation. So you can avoid a lot of the field experiment, which costs a lot of money, a lot of time. So science speed up dramatically because of that. But of course, real experiments still will be fundamental. But the way we do it is completely different. However, in classics, right, you have classical mechanical problem. You somehow guess the empirical solution. Then you write down equation according to phenomenological phenomena. Then you go back to test again, and then you pick up a parameter which is more or less right. Pick up a few important parameters, and then the last is the partial differential equation. Okay, so PD guys are very, very tough. It's one of a bridge related to science and mathematics. Now, there is also a challenge in the sense that the subject of PD itself, because in this process, computer replaced by, and you can ask whether or not PD theory will be necessary in whole science. And that is something I don't like to clear either, right? I'm working with it, but don't worry about it, yeah, because I will continue. The last one is also a challenge. As I said, for example, Kloster's recent paper on existence of black hole in Einstein's theory is about 900 pages. Okay, his earlier paper was Serge Kleiman of stability of Minkowski spacetime was 500 pages more, and about ideal realistic relativistic fluid Euler equation, he published, developed sharp waves, was about 700 pages. Now, anybody, if you read these three papers, you already owe by then, and you already lost all the energy to continue what you're going to do. So, if mathematics or partial differential equation continue this way, I have little doubt it will survive, right? Because it's clearly not. Unless we feed a lot of new kids, yeah, our kids, baby kids, with a lot of chemicals or genes start changing, they really become smart. Otherwise, I don't see or build up mind, some computer chips or something. Because how can they do that? Just not visible with this kind of growth of a paper. So about the second issue, so here is a comment again from Harold, famous comment. A branch of science, life, will full of life as long as it offers abundance of problems. Or this is something comfort, or this is something a basic guideline for young people when you choose a scientific research direction where to go. You should choose, of course, you always follow your interest or love. That is very important. If something you don't love, don't do that. Okay? So you always follow your passion, of course. But besides that, you probably should be a little bit intelligent in the sense you choose something you have a lot of problems to work with. If you go into a field, essentially it's exhausted ideas, it's probably not a great idea to continue further. Okay? No means nobody should go. Some people still will go because some people really love that kind of thing. But for most people, probably that is still a general guideline. But for us, we always should think about that, whether or not our field will survive, and to see whether or not. Now, from partial differential equation, there's no question that in pure mathematics seems more popular. But in applied mathematics, the rule is changing. The computer replaces a bigger portion of that. It does not mean the philosophy of partial differential equation or something will change. Professor Lebrit pointed out that you probably should expand it to statistics as well. In other words, if you combine with other disciplines of science, such as statistics, now become extremely important, then you still have a lot to do. Okay, so that is something, another paradox that I love very much, because Peter Lux is a beloved faculty at the Courant. And the paradox is, as I said, the professional literature or mathematical paper, because the text files getting so long these days, a longer and longer exponential growth in knowledge. How can young people keep up with that? And Professor Peter Lux has a very optimistic point of view, and he basically said, as a helpful view is, if you're doing something, mathematics, for example, you walk on the street, some people come up to you, you should be able to explain. I'm not sure I can do that. But at least that it means that you should be looking for some simple, beautiful, fundamental, essential things, okay, instead of buried in technical issues. And that is a very interesting comment, because it's really important for educators. Because science is evolved so quickly, what kind of education are we going to do? From elementary school to middle school to high school and to university. And that is a fundamental question, because that will be the future of science. And I think that is important also, even though I'm talking about the challenges of the partial differential equation. But this is a general thing. Okay. Now I talk about these days, in order to solve any meaningful problem, you have to combine many disciplines of science and mathematics. And that creates a problem. Because, as I said, you even find it very difficult to explain to your colleagues what kind of thing you do. And about 10 years ago, Gromov already described that we should create somehow somebody can intervene between pure mathematics and general applied science. And cross-fertilization of the idea will be crucial to the health of the science. In fact, the issue, if you people look at the future of mathematics, an article written by Andrew Wei, 1950. It's a beautiful writing, and he seems to have a very pessimistic view, however, about the future of mathematics. But now it's more than about 60 years later, it seems mathematics appears even more in other places you never expect, such as medicine, biology, ecology, climate, material science, everywhere, and which actually 50 years ago you never expected it will ever happen. So, however, there is something as a professional mathematics that seems to become necessity, and that it becomes very important for interdisciplinary research. And that one of the force of this IMS is fertilization, exactly across the interdisciplinary researchers. So this is a general comment, and I thought this is interesting from the February issue of the IMS. But the mathematicians in general divide into two categories. Those really deep down to do hard, dirty work, and those have a wonderful point of views. Okay. So this is already something, you cannot say one is more important than the other. Okay, so let's not argue about it. It's all the philosophy, what you like or what you don't like. But I thought this is an interesting article, and you can take it too. Okay. So I had to talk about the general science and general comments. So let me finally come back to the partial differential equation. Now in classics, that we know that it has a very unified subject, like the study, the well-posed things. And the science is evolved, and it's no longer fit, the challenges of new challenges and so on and so forth. And so, what is the new seed of studies of partial differential equation? Okay. So below, I'm going to express a couple of my personal things, which I don't think it's particularly my personal. I thought that with help of my colleagues and with my own experience over the last 25 years in that field. So I come up a few things. One of the new unified subject in PDE, I say, is study the singular behavior of solution. Singular behavior of solution. Why? what is singular behavior of solution? We can talk about that. Imagine if the solution described by some function which is changing slowly in spatial direction and time, then why you bother? You just use computer, you can tell practically everything. Okay, you can wait a long time to understand the phenomenon because it's never really changing much. Okay? And when you're doing all the well-postedness and so on and so forth, it does not make very much sense. However, singularities, as the professor slowly pointed out, the defect is actually interesting. The people become interested because they have a defect. Okay? And here is a few examples, such as defect in nickel crystal. There's vortices in ocean atmosphere dynamics, attractor of dynamical system. These are fractals, and giant vortices in Bose-Einstein condensate. A few examples, tons. But these are somewhat concentrated phenomena. Okay, concentrated phenomena. But you have more. In general, singular behavior could be true singularity, intrinsic, such as like conical surfaces and so on. And could be actually not really a topological or other singularity, just simply energy, momentum, mass, whatever is highly concentrated in this spatial location, very much like a solid, for example. And what could be actually due to the third factor, which is the oscillation. Oscillation could be in physical space, position, or could be in phase space, particularly in wavelength, people really dealing with a lot of phase space decomposition. It's very, very important, oscillation, and understanding that. Okay. And here's more examples of the singularities, such as a black hole in general relativity, I already mentioned. Where you can say is the concentration phenomena, because everything is sucked into a point. The mass concentration is going to become infinity there. And pattern formation, sometimes could be not, sometimes you can find it very interesting. Could be a spike, sharp interface, filament, not the structure. You can observe in a lot of condensed matter physics or in biological pattern. Okay? But these are characteristics of the problem you want to understand. Why the singularity is interesting? Because they reflect the characteristics of the problem. Because in the smooth part, everything looks same. They are boring. Okay? Because these singularities, it's hard, yes. But these really reflect the characteristics or fundamentals of the problem. Okay? And for oscillation, there are a lot of tools developed, multi-scale, multi-physics, and so on and so forth. So, there I think it has two things. One is study concentration, the other study oscillation. The point of view, I think, more than 10 years ago, Louis Lyons at the International Conference or something, he already pointed out that these things will be extremely important to study. And indeed, over the last 10 or 15 or 20 years, that mostly go in such directions. Okay? And there are a lot of development called hydrodynamics, but a lot of them to solve. You see, if a world is completely random, the probability works very well. If a world is well ordered, then anything described very well. The difficulty in a lot of issues is partial ordered, partial random. Okay, and that introduced these are purely so the highly oscillating, purely well distributed random phenomena. They have a lot of tools, and Wiggin measures, and mathematically edge measure, macro-local measures, and these Young measure, defect measure, variable. These are more geometrical objects. These describe a concentration in, say, various dimensions. Could be 1, could be 0, could be anything between 0 and 1. Okay? So there are a lot of mathematical tools developed. But the issue now is to couple them all together. That become very difficult. Okay? So the challenge is multi-physics, multi-scale, coupled motion, and mixed fluid motion. You may have object in fluid and so on. These are really a multi-scale. So there are tons of partial differential equation problem, tons of engineering problem, and tons of problem from science. Seems to all have very similar nature, in fact. For example, you have a lot of defects, and then what's the hydrodynamics of that? That reflect the mean property of the material, and that become very, very challenging, and so on and so forth. So I simply want to stop my lecture here. And I hope that I did cross a couple of points, well, thank you very much.
Well, before we ask Professor Lee the question, I'd like to present to him the total appreciation. So this is a gift from the institute. So I'm sure Professor Lee will be very happy to answer. The civil dialogue was when was it?
That was about, let me see, it's about 7 years ago. Yeah.
But it was long after you
No, actually it was same year. I was a full professor, 89 and 88 at Chicago. Several professors.
So I remember that you also give a lecture, right?
Right, that was hard.
And then you said it's going to be very difficult to give a lecture to
Right.
the non-specialists, right?
Yeah.
But after listening to this lecture, I don't think it should be difficult for you, right? So anyway.
Okay, thank you very much.
So anyway, I'm sure you'll be happy to answer any questions.
Yeah, okay. Oh, okay. When I asking for answers.
Oh, yes.
So when a graduate student comes to you to pick a problem, which one would you suggest?
Well, I usually will ask him to come up with his own problem and let me to make a judgment to help him to make a judgment. And that will be best way. But if he really cannot come up with a problem, then I probably will, give him some direction. Because it's always better to ask the student himself. But general principle is, first, it's always choose the problem, of course, you like it, right? If you don't like it, probably you won't spend much time anyway. and secondly, it should be always important in some way. But how can you tell important? Well, you should look at important people's paperwork. Okay? They usually express certain directions and so on. Now, if a problem from applied science, if it is important, even mathematics involved could be simple. But if you find the answer, it already has very high value. But if mathematics involved is highly non-trivial, then you have double of work. You not only solve practical problem, but you also get a wonderful mathematics. So I think that the problem starting point should be always valuable, important in practice. Among them, as a mathematician, I always like to choose a problem which, from a mathematical point of view, is highly non-trivial. If something which you just say, go to library, find the differences, and get a problem, then you should ask a lot of the students to write a math thesis or study report instead of doing research, because it's already there an answer, even though the solution may be useful for other disciplines, but as a mathematician, probably not enough. So you always balance between these two. Yeah.
Now this answer is generic.
Generic.
For any PhD student.
Yeah, yes.
I'm going back to S.S. Chen's comments.
Yeah.
You are recommending a wife.
Okay, okay.
So which wife would you pick among the PDEs?
Oh, I'm an older guy now, so probably the taste may not be ideal, but I will choose certainly the one which I like. Okay, so that is a simple answer. So individual faculty can only somehow pick up things they're best at it, and they know exactly what's going on, and they know exactly where the difficulty is, where they probably should go, and that at least won't waste too much time for a student. You shouldn't give a problem which you have no idea at all to the student in the first place. And it's just for fun. You say, well, you should think about but don't bet life on for this problem because yourself have no idea. Okay, So usually you choose a problem, not means you have an answer, but you know in that discipline, that direction, and you know it has a lot of future. For me, the principle of choose a direction or choosing, I will follow more or less the Herbert or Gauss or these people basic laws in science that you always choose a good direction that has a lot of problems to solve. But on the other hand, you always negotiate yourself with your own ability, your own speciality. You should never forget your own speciality, individuality. Okay? You shouldn't say, well, look at this mountain is higher than the one you stand on, and you go there. It's always a mistake. You are always special. So, but on the other hand, you should be open-minded from the beginning. Okay, so it's good balance.
Any question from the students? You have your missed chance asking the big professors questions. And it's some of the students, right? Am I right?
I hope I answer your question.
Okay, very good. Yeah.
Professor, one of the questions that you just showed, following the Euler and the other one, the partial differential equations, which is yet unsolved. It looks quite sweet and small and looks easy, but like the way the difficulty which you exposed, it seems as if there are pages and tons of pages involved in that. I don't know. I mean,
Navier-Stokes actually for this problem, there are quite a few papers. There are much shorter papers, not like the ones I explained, like 500 pages, 600 pages. No, for Navier-Stokes maybe longer than maybe 50-something pages. Okay. Probably you only need to read 4 or 5 important papers here. And then you can essentially say that you know more or less the most experts know about the problem, because the ideas are very, very few. And why it is so, it's become more philosophical issue. And the problem is fascinating, that is why.
I'm too old to be a student again, but I want to ask you, you talked about PDEs being central to, to mathematics or mathematical analysis, right?
Yeah.
And later you mentioned that now you think the study of singular solutions or singular behaviors will play even more important role in this subject.
In the subject of partial differential equations.
So then you does the study of singular solutions or singular behaviors, what areas of mathematics you think this is going to impact? Or what?
Well, because one of the simple examples is the Pellman solution to Fanghua conjecture. It's a non-linear partial differential equation. The key issue to understand is the whole singularity development and how to do all of that in certain. So understanding the singular behavior, understanding singularity is very important. And Navier-Stokes is basically saying if you believe something that happened, and then you would ask yourself what type of singularity can develop in Navier-Stokes equation. And that is a problem that nobody knows, and that is a problem. If you know that Navier-Stokes can only develop certain type of singularity, then you try to go over using every possible ways. The issue is we don't know what type of singularity can produce by Navier-Stokes equation. For Euler, it will be even more difficult. As you see, every scale, if you have a solution to Euler equation in that small box, you can dilate it to any small box, still will be Euler equation solution. That means you compose it, make a solution arbitrarily complex. However, given one, you have a given complexity. And whether or not it will have certain spark in space-time that will really go disaster, we don't know. And that is the problem.
What is your problem? Mathematicians have like one partial differential equation. They have one problem or two problems. Can you, in relatively simple terms, describe your problem?
So I work a little bit here, this equation, not a little bit here, but not these two. Here I'm interested, little work, but not much. I spend a lot of time on this discipline. I know something going on here. Now let me tell you, I know quite a bit of PDE, practically know all these equations. In what sense? In far away picture. But if you look at me, say, I know exactly what's happening, I only know a couple of them very precisely. So it's like when you walk on the street as a person, people might talk to you about, music, arts. You might know something about it, but not means you are expert. So Chinese have a way, of course, called the general shuya. Mathematics is similar, that you need some general picture, a general education. So how can you get it? It's a very simple principle. Each time you're doing something, you know exactly why you're doing that. If you ask this question, and your work, what's the relevance of your work, say in the field you work with, or what's the relevance of your field respect to larger field or general science. Not means every day you think about it, then you won't have time to think about your problem. But once in a while, you should go back, think about these issues. And if so, you won't get completely lost there. And that means you, besides understanding your own direction and field, you keep learning many other things. But this is like, as a basic human being, that you read a lot of novels, read a lot of history, read a lot of literature, music or something, it helps you in some ways. You may appreciate more what other colleagues does. You may appreciate what other scientists does, and so on and so forth. And that is very good. That is very good. So, yes, I can only do specifically only 2 or 3. I think recent years I spent quite a bit of time on this. Okay, I spent quite a bit of time over the last 15 years on this. But I practically know everything about this equation. I should have said practically, because not everything. I'm interested in this is one of them now. I know what's going on here, but I know very little how to do it. So, you can tell. But that's about it.
Well, any more questions? If not, please join me and thank Professor Lin again for his wonderful